Wczoraj mieliśmy trochę o Linuxie, dzisiaj chyba też będzie. Jest na prezentacji Linux napisane, no to cieszę się, że Krzysztofie o Windowsie dzisiaj nie mówisz. No i wczoraj udało się rozwiązać nasze konkursy kryptograficzne. Wow, bo były z tym problemy, a to były takie dosyć proste szyfry. Potem damy informację, co to były za hasła, jeśli chcecie wiedzieć po prostu, jak to było. I co? Już tobie nie zabieram więcej czasu. Zaczynaj proszę.
Hi everyone, my name is oh, sorry. Hi, my name is Krzysztof Biegański. I'm a senior software engineer at Antmicro, and I mostly work on open source Verilog or system Verilog tooling. And lately, I've been working on speeding up OpenRoad, which is like a open source Verilog to Silicon toolchain, and you may have got a glimpse of that yesterday. There was a really cool presentation by Piotr about building your own computer, and he actually used that toolchain to get the final chip on silicon. So that was really cool to see. So yeah, it's nice to contribute to that a little bit. So yeah, and I'm going to be talking about performance analysis and benchmarking. And this is something that also was touched upon yesterday. I think it was Philip's presentation, the first presentation of the day, but that was more from like a kind of DevOps perspective, with looking at the performance of the whole system, and this is more from like a programmer trying to speed up their program perspective. Okay, so without further ado, let's talk about performance. And the rule number one of performance optimization is to always measure, because you cannot really do some changes and assume that they will bring you some speed up, because I don't know, this data structure is faster than the other one. That's not the best way. You always have to measure it. And there's lots of stuff that we could talk about here. We could talk about latency or network throughput. There's lots of things you could measure and optimize, but today we'll focus on some stuff because we cannot do everything. We don't have all day. So we're going to focus on CPU-bound applications and kind of CPU throughput, basically. And focus on native code, so no interpreted languages like Python or something like that. We're going to talk about user space, not much about the kernel, and about x86, 64, although this stuff does transfer over to other architectures like ARM or RISC-V. And this is just because I've been working on this stuff, so this is why we're going to focus on this. Okay, so let's talk about benchmarking. Benchmarking is a useful tool for determining if a certain solution is better than the other, right? So it's very simple. We run our program, we measure different solutions, and we decide which one is better. So let's try and do that. Let's run. I have this little program here that generates Sierpiński triangle. It's very simple. But less than 100 lines of code probably. Let's measure how long it takes to do that. And we don't really care about the output really. Let's just do something like this. And we see a few numbers pop up. It's the good old time command. The most important here for the user really is the real time, not user, which is confusing. Real is the time that we actually spend waiting for the command. User time is the CPU time that was spent in user space, and sys is the CPU time spent in kernel space. So those are important, but ultimately the user really cares about the real time, right? So let's just look at that. Okay, so now let's also try a bit. Let's try a bigger triangle, because it'll be a bit more interesting. Okay, so, but this is kind of, one number doesn't tell us much, so let's try and running this in a loop. Hopefully I don't screw up the syntax here. Should be okay. Oh, sorry, I missed the argument here. Okay. So I'm gonna run a few times. And you see that the numbers are sometimes smaller, sometimes larger. And there's kind of this sort of noise that's happening. And that's not really helpful. It's a really bad thing for us if we want to measure how good something or how fast something is. And well, one thing we could do is we can, like here, we can take a bunch of samples, run it a bunch of times, and take the median or even the minimum from this, and then compare that to other solutions, and that's fine. But well, I would say you can take the median. Don't take the mean. The mean is not a great option because you have to worry about outliers, stuff like that. So the median is usually safer. So yeah, we can take a bunch of samples and try it that way. But well, this program is really fast. Like it finishes really quickly, so that's not a big deal. But if you have something that runs for I don't know, an hour, then like taking 10 samples of that is 10 hours, which is just really slow and unacceptable if you want to iterate on a solution. So let's talk about this noise. What are the sources of it? Well, there's interference from other processes, right? Your program isn't the only thing that is running on your machine. There's a bunch of other services, like background services, that all compete for the resources for CPU. So one thing you could do is disable a bunch of processes and background services. Also, the CPU has variable throughput, and it isn't that important in like a small program like this, but it is important. Like the CPU doesn't run at the same frequency all the time. So sometimes it slows down, sometimes it speeds up, and it's pretty random. There are also caches, like a file system cache. So the first time you access a file, it will be much slower than when you access it the next time. So you have to keep that in mind. Sorry, I jumped the gun here. So let's try and disable a few things in the kernel so that we can kind of get rid of this noise for a little bit. There's this nice file system called sysfs, which has a bunch of stuff that is useful for us. So I think it was maybe not this. Oh yes, it was here. And we have, yeah, I can't really remember it, so I'm just gonna use, okay, right, so yeah, there's a bunch of files in the sysfs file system that kind of you can use to configure your CPU. And one of the things that you can configure is the frequency scaling, which is this kind of feature of Linux which manages the frequency of your CPU so that it doesn't always it doesn't always run at a maximum frequency, which is important if you have like a laptop or a mobile device. You want to conserve battery, so this frequency scaler does that. It manages the frequency so that if there isn't a need for a higher frequency of the CPU, it scales it down. And there are various different algorithms for this. They're called scaling governors. And the one that we care about is performance, which will try to keep it at a kind of maximum level, sort of maximum, and we're going to talk about it in a second. But the way you do this is you just write the performance to these files called scaling governor for each CPU. CPU is really a thread hardware thread, but it's called CPU in Linux. Right, and I think there was even, yeah. Now I can display these. Okay, that didn't work. Doesn't matter. There's another thing I want to disable, which is Turbo Boost. And this is Intel's marketing term for this, but AMD has its own thing like that. Turbo Boost is basically, if you see look at a CPU spec sheet, you see that there's always like a base frequency and a boost frequency. And if the CPU has more work to do, it boosts up to the higher frequency. And this is really nice. It's really important. It really gives a really big boost. But again, it's random because it depends on things like temperature of the CPU, because it cannot do that for too long, because otherwise it would just go up in smoke, right? But when we're benchmarking, we cannot really predict how much this will kick in or when it will kick in. So we just want to disable it for the sake of reducing noise. So I just did like this. Like this is Intel specific, but there's AMD probably has something similar. And let's try and run this again. And now you see this is much, much slower. But the noise is a little bit better. Like percentage-wise, it's really much better now. So this is a bit more reliable, and you could do some more stuff. Like you could disable hyperthreading. I don't have hyperthreading here, but hyperthreading is basically when you have each core of your CPU can do multiple threads of execution at the same time in parallel. But the thing is, it cannot really do that all the time. It can only do that if the operations in each thread don't overlap, which again we cannot really control. Sometimes it happens that they don't. Sometimes they do. So it's random. So let's just disable it. This one is interesting. You can pin your process to a certain set of CPUs or cores. You can use this, again, a file system in Linux called CPU set, but don't really use that. It's very cumbersome. Just use cset, which is a script for that. You can find it on GitHub. And you can, let's say you have 8 cores on your machine. You can pin your OS, like all the processes on your OS, to the first 4 cores, and your application to the other 4 cores, and then you get basically no interference from other processes. Yeah, and another thing, like I said, I want to focus on CPU throughput, but perhaps you're worried about I/O performance. So before each test, you should clear the file system cache, for example, or warm it up, depending on what you want to test. But you cannot mix those. You have to be aware that what exactly you're testing. You cannot just you have to worry about it, because otherwise you will have significant outliers, because the first access to some files will be much slower than the subsequent ones. So there is a bunch of noise in your data that way. And also you can use tempfs, which is RAM-based, instead of like writing to a disk. And this all depends on the use case. This is not an exhaustive list. It really depends what you're doing. Like if you're doing network stuff, then this is not really, most of this isn't relevant, right? More worried, if you're network bound, you're worried about different stuff. Okay, so that's benchmarking. But now let's do something a little bit more interesting, which is profiling. And profiling is a way to look at your program and see which parts of it take up the most time. And that doesn't necessarily mean which parts are the slowest, because you may have a function that is already as fast as it possibly can be, but it's called a bunch of times and take up still like 90% of your program. So it's more about which functions in your program take up the most time. So this isn't really an answer that, okay, you should speed up this function, because maybe you cannot. And maybe the answer is to reduce the number of calls and cache some stuff. So this is basically just a way to look at the program and try and notice optimization opportunities. And also, if you're like new to a code base or something like that, it can help you understand what's going on in the program, because you can see which functions call each other and things like that. And also which functions are more important, because presumably if a function takes up more time, then it should be more important than ones that don't, right? Okay, so let's do this using perf. Perf is kind of the go-to profiler on Linux. And for good reason. I think it's probably the best tool for the job. There are different profilers, different approaches to this, but I think perf is the best one. And sorry, let's do our little program here. We just say perf record, we run our command, and then we can see that there's a perf data file here on the left. And yeah, this is basically the capture a profile of your program that we can now display. Perf report. And it looks kind of like that. On the right, you see symbols. So those are functions in your program. And on the left, there's overhead, which is how much, percentage-wise, how much time it took, how much time of your program was spent in this function. So for example, like row took up almost 18% of the time. Then we have command, the second column. The command is kind of just the command that you ran. It's not hugely important here, but you can actually run perf on the whole system, for example, and then you want to be able to distinguish which command you're looking at. And shared object is just the elf file in which this particular symbol was defined. And you can see there's this is from my program here, and then we have libc, and we have some kernel functions. But this kind of doesn't really give us much context, because we just see a list of functions and how much time they took. So let's do something a little bit more interesting, which is let's record call graphs. And we do that with adding this -g flag to perf record. And yeah, now you see there's a little bit more stuff happening. There are two columns with percentages on the left. Children here means how much time this function took, including the functions called from it. And self means how much time this function itself directly took, so excluding functions that were called from it. So let's say here we have main, right? It's a pretty obvious example. The main function doesn't really usually do much. In this case, it doesn't really do anything. So even though pretty much everything happened, like 99% of the time was spent in main, or its children, there was no time spent in it itself, because we just immediately go to a different function. Like, yeah, so for example, if I expand this, or maybe no, let's expand this. If I go to main, expand main, I see functions called by main. And we see that it called generate, and generate called row, and I can expand this further and further. So that's nice. There's also a different kind of way to look at it. If we do -g callee, and we see the graph is kind of, or the tree is inverted. So we see kind of the innermost functions. And now if I expand, like if I expand main, we just see that it was called by libc start call main, so that's not really useful. But I can expand generate, it was called by main, point was called by row, and generate and main. And you will see that this is kind of weird because there's a few kind of artifacts here, like for example, well, if we look at point, point seems to be called by row and generate, and that's not the case. It was only called, it's only really called by row. And you have to be aware of this stuff. Like perf is not a perfect tool. It's not really precise. It's kind of approximate, and you have to keep that in mind. It's still very useful, but I'm gonna talk about how it works in a minute. There is some weird stuff happening in these reports, so don't be surprised. And there's various stuff that can influence this, like you could have optimizations, function inlining that causes this. Yeah, so keep that in mind. One more thing that you may be thinking, okay, this is fine, seems useful, but it's kind of boring. Like it's just a bunch of text and numbers. What can I do to kind of visualize it? Well, a nice tool for this is, or kind of type of graph for this is a flame graph. Let's try and generate it and display it. So it's not very impressive for this little program, but I'm gonna show you a bit more. Let's just kind of, hopefully you can see this. Okay, and maybe I'll show you just a more complicated example from like a real program that I worked on. So here it is. So you can see this now does seem like a flame graph, like the name is justified now. And you see there's a lot of stuff happening here. And the way you read this is the horizontal kind of axis is the amount of time that was spent in this particular function. So, you know, again, we have main, that's really long because it's most of the program. We also see, and then the vertical axis is the call stack. So if we go from here to here, this function called this function, and it called this function, and so on. And yeah, this is just basically a huge call stack up here. And again, this seems nice. Like immediately you can see the main sort of areas that may be of interest for you. You're gonna have to really worry about numbers that much. You just look at it visually. You can tell that something is slower or faster. But we also don't see much detail here, right? There's just, you cannot really read this. So what you can do is actually you can zoom in. So let's say we're interested in this little function here. We click on it, and we zoomed in into this function. We can see the functions that were called by it. And yeah, and this is just, again, a way to see what takes up the most time in your program. There are also various GUIs for perf. Like the one that I'm going to show you here is Firefox Profiler, which is usually used for profiling JS in Firefox, I guess. But you can actually open perf traces, let's say, in it, and use this nice little GUI that you have here. So you don't have to use a terminal for this terminal UI. You can have an actual human UI, right? And there's also like nice things like flame graph, something like a stack chart. So there's like a timeline. You can just zoom through your program and see what functions were called at what time. So it's really useful stuff. And this is Firefox Profiler, but there's an equivalent for Chrome or Chromium. There's also standalone GUIs, Hotspot and sysprof. So probably best to start with something like this, but check it out if you're interested in using it. Okay, so that's perf. And the interesting thing about perf is how it works. And perf is what's called a sampling profiler. There's a few different ways to profile a program, but sampling is is, in my opinion, the best one. And the main reason for that is its low overhead. So the way it works is your program, when it runs, it's stopped every once in a while, like let's say every few microseconds, that this is configurable, how often it stops. It gets stopped, and then perf captures certain information from your program and then analyzes it later. And this happens like thousands of times per second. And this, the main advantage here is that it's low overhead compared to other solutions like instrumentation or simulation. And because of that, you get reliable results. So there is no skew in that if perf says that your function took up 5% of the time, then you can trust that. But if you use different profilers, you get numbers that don't really reflect reality, because they skew the results and they introduce overhead that messes up with the results. So perf is not an exact profiler. It's kind of random. It's a statistical approach to profiling. But overall, if you capture hundreds of samples or thousands of samples, statistically they make sense. So that's in the given percent that you saw in the perf report. That's the percentage of samples, not of actual time. So because this is kind of because it's not exact, that's why you can see some different weird artifacts in the output. So I think when you're using a tool, I think it's nice to know how it works, at least a little bit, because then you understand the limitations of it and why something doesn't happen as you may expect it to. So perf itself is actually just a front-end for this kind of subsystem in Linux called perf events. And perf uses this system called perf event open to talk to perf events, and then uses a ring buffer in user space to get information from it. So perf events captures some data, some events, and writes to the ring buffer. Perf reads that. And the thing here that's interesting here is that the ring buffer, it's a fixed size queue. So if perf cannot keep up with perf events, like perf events writes more than perf can read, then some events are dropped. And sometimes perf will tell you, I dropped this many events because I couldn't keep up. And perf events uses a bunch of different sources of information, but for profiling, it uses performance counters, which are it's the PMU, performance monitoring unit, I think, on the CPU. And what the PMU does is it kind of keeps track of interesting performance-related events on the CPU, like cycles, cache misses, branch misses, cache hits, branch hits. It's also kind of vendor dependent, different, and even model dependent. Different CPU models will have different stuff there. But you may be thinking, what does that have to do with sampling? It seems like it's unrelated. And perf, or perf events really, uses a nice little trick that I'll show you here. Let's say we have a 32-bit cycle counter on the CPU. and it counts up every cycle. We have our app running for some time here, and at some point we get to this situation where the cycle counter is at 2 to the 32nd minus 1. So what happens now? Well, we get an overflow, and the overflow triggers a CPU exception, and our program is stopped, and the control goes over to the kernel, and the kernel gathers a sample of our program. So this happens over and over again, right? The program runs, there's the overflow, the kernel takes over, the app runs again, the kernel takes over because of the overflow, it gets a sample, and so on and so on. And this, in this case, would happen every 2 to the 32nd cycles, which is quite a lot of cycles. It's 4.2 billion, right? So that's not very useful because it's every second on a 4.2 gigahertz CPU. So that's not nearly enough samples for the statistical approach that I was talking about. So the solution here is to set the counter to 2 to the 32nd minus some value. And this value will be the number of cycles between samples. So if this C is set to 1,000, then every 1,000 cycles we get a sample. So that's basically the way it works. There's probably some more details you could delve into, but more or less get the idea. So that's the sampling part, but we also need to look at, it's nice to look at the analysis part, like how does perf actually know what's happening, because it doesn't know anything about the program. It just sees a bunch of binary data, right? That cannot really, the only thing that it knows is where the stack is and what the registers are. So let's remind ourselves how calling a function on x86 works. So we have this situation, we're in main. The instruction pointer, RIP, points at main. And then we are calling some other function. And on x86, we need to put down function arguments. We need to put down the return address so that we know where to return after we're done with this child function. And so with the return address is just the instruction pointer. So we store the instruction pointer on the stack. And then we update the instruction pointer to the new function. And the return address now points to the old function. Or the return address on the stack points to the old function. Now there's this other little register called RBP. And this register, we also store it on the stack next to the return address. And then we have local variables from the function, doesn't really matter for us. And the next thing we do, we update the RBP register, which we call a frame pointer, to point to the previously stored RBP, or previously stored frame pointer. And then we do the whole thing again. We call another function, we put down the return address, we update the instruction pointer, and then we store the frame pointer, the current frame pointer again. And again, we update our current frame pointer to the one that we just stored. And we do the whole thing again. We update the instruction pointer, and we store the frame pointer. We update it to point to the one that we just stored, and we get to this situation. And now you can see that there's an interesting thing happening with the frame pointers, or RBPs. They kind of form a linked list. So let's try and reconstruct a stack from this information. So first, we know that in the RIP, the instruction pointer, is the current source, current code location, right? So we know that it points to the current function that we're in. So we can look at that, and we can see that we're in G, and that we get that from the symbols. We know that this is the symbol G. And yeah, so we can put G on the reconstructed stack. Then the next thing we do is we look at the frame pointer. And the frame pointer looks at the frame pointer that was, points at the frame pointer that was stored previously, and we know that next to it is the return address. So the return address, again, it's the old RIP, so it points at the previous function. So we see that it points to h, so we can put h on the stack. And we do this again, but now we look at where this stored frame pointer pointed to. It pointed to the older stored frame pointer. And next to that one is that return address. So we can, we know that this return address points to the older function. And we look at that, we see that it's f, we can put f on the reconstructed stack. And then the whole thing again, we look at the stored frame pointer, it points to the previous stored frame pointer, we know that the return address is next to it, we see that it points to main, we put main on the reconstructed stack. So that's basically how it works. If you kind of missed that, doesn't really matter, it's not useful that much for using perf, but it explains a certain limitation of perf. Like perf by default uses this RBP register for tracking where it is in the program. And the thing is, many compilers optimize the usage of this register out because it's not really necessary usually. So like GCC or Clang will optimize it out. So you have to compile your program with this flag fno-omit frame pointer, which will in theory slow it down a little bit, but it's not a big deal. Like back in the day, it was maybe an important optimization because like back then you had like 4 registers, general purpose registers, and this freed up one register to be, so you get 25% increase in registers, so that's significant. But nowadays you have like 16 general purpose registers, next 86, 64. So one more doesn't really make a difference, especially with how CPUs work nowadays. So yeah, like I said, it does make a difference, but performance-wise, but it's not a very huge difference. And for profiling, it's useful to disable this optimization. There are alternative ways to get like call graph information, but like for example, you can use Dwarf, which is the standard debug info format on Linux, but it's a bit slower and it gathers lots and lots of data. Like it's, I think maybe the perf data file that you get from Dwarf, it's like 100 times bigger or something like that. But there are alternatives that are available, which is important and nice to have. So that's profiling, and I also wanted to mention tracing. Tracing is a pretty big topic in Linux, and this isn't really an exhaustive picture of it. But we're gonna focus on perf, and I don't really have time to get into this image too much, but we're gonna talk about tracing using probes. So let's try and do that. And for that, you unfortunately probably will need sudo or like elevated privileges. Probes are kind of like breakpoints, but for tracing. So you can tell perf that you want a breakpoint in this executable at this function. Oh, sorry, I missed the command. You say perf probe -x, which is executable, and then we pass in the executable and then the function that you want to probe. And it says that I added some new event. And we also want to add another probe at the return of this function, so at the end. And yeah, so now let's record our event. And we do that by saying probe. I think something like this should be working. It's something like this. Okay, so it again generated a perf data file, but it's owned by root, so let's change that to make it easier for us. And now we can run this, for example, and this will display all the things that happened in order, so all the events that I wanted to track, which is basically the call of the row function and the return from it. But this is not that useful. So let's do something a little bit more interesting. We can do this nice command called, well, we can do this -g flag with perf script, which will generate a script for you. And here we have, it's basically, this script contains functions that are just callbacks that are called at a certain time or certain point in the trace. So trace begin obviously at the beginning of the trace end at the end. So this is where you do like initialization and writing to files or something. And then you get this function probe st row, which is called for each event where this row function is called. And this already has some default stuff. Also, we see the function for the return of this row function. And this already has some example code that you could run. But let's maybe try something a little bit more interesting. I have a script prepared here. And this is a really simple one. It's just kind of takes the minimum time that this function was executed in, and also plots all the execution times of this function using like matplotlib. So let's, oh sorry. So let's run it. So it printed out the minimum time this function was executed in. It's 100 milliseconds. And also we can display the plot that was generated. I think it's like this. And yeah, it's mostly flat. It's basically all the functions. I hope you can see this, but it's mostly the same time for all the all the calls to this function. But there's one little spike towards the left that's interesting. So maybe I was thinking maybe this is like a context switch happening here. So let's see if that's true. You can track many different events in perf. You can use perf list to list all the events that are available to you. So there's like, you know, branch misses, cache misses, bunch of cache events. The one that we're interested in is sched. It's called sched switch. Oh, sorry. I misspelled it. Okay. So now this will also keep track not only of my function, but also the context switches that happen during the execution of my program. And I have another script that I can run. Sorry, it was time row sched. You can see that there were some context switches, and the time spent with a switch is much slower than if there was no switch. So let's display the plot that was generated from this. So there was lots of context switches. I'm actually surprised there was this many. I think there's something running in the background messing it up. And yeah, the orange lines represent the context switches here. And you can see that these, sorry, not really the context switches, but the calls to this function that were interrupted by a context switch. So you can see that the slowdown is quite significant. So this is just an example of what you can do. This is like a toy program. You can't really do much with analyzing it. So Yeah, so basically, like what I can tell you now is just to go forth and measure whatever you're working on and test it and benchmark it. And remember these few basics that I talked about. Take many samples, reduce sources of noise as much as possible, use a low overhead, high resolution profiler such as perf. I do not recommend using something like gprof or valgrind for profiling. Visualize the data because you may see some patterns that you otherwise wouldn't be able to. And just experiment. That's what I hope you to do. That I hope I encourage you to just check out perf and all the stuff that you can trace with it and see what you can do with it. Okay, so that's it from presentation. Thank you. I guess it's time for questions now.
This scene is like a maze sometimes. Your presentation was focused on benchmarking CPU-based programs. Are GPU-based programs much different for testing?
That's a good question. I've never profiled a GPU program, but there are profilers for GPUs, and I think there's two parts that I see there. One is the part where your CPU is communicating with the GPU, so there's a bunch of overhead with transferring data and waiting for the GPU to do something. So that's I would imagine that it's similar to something like waiting on the disk to do something. So it's kind of like I/O thing. On the GPU itself, you only have small programs called shaders, and you can profile those, I'm sure, but they're not too complicated. So unlike like the flame graph that I showed you earlier, that one is like huge and there's lots of stuff going on. If you profile a shader, it's going to be more like this for this toy example here, pretty small probably. So yeah, so you can do these things for GPUs, but I cannot really offer you any tips because I haven't done that.
As follow-up to GPU question, how about TPU?
I've never done that, so but it's probably similar to a GPU.
Okay. How is sampling a low latency method? The process has to be interrupted and eventually execute a perf code, which sounds like an expensive instrumentation.
Yes, yes, that's true. And if you have some latency critical system, then maybe the best solution is to write some custom instrumentation for it and just use like CPU registers directly to read time and things like that. For that use case, like depends what you're doing, but for that use case, you may have to roll your own stuff.
Does any of this work in Zephyr?
No, because this is a Linux feature. So, like I said, perf events, which is the main thing that is responsible for everything that's happening, is just part of Linux, and even perf itself is in the Linux source tree, I believe, like the front end for it. And Zephyr may have something like that, but I'm not aware of it.
Wouldn't it be better to use a hardware accelerated tracing like Intel BTS or Intel PT instead of the sampling?
Yes, some cases it would be better, but they also have their own limitations. Well, first of all, it's vendor specific, so maybe if you're using Intel, then that's fine, but if you're using a different vendor, then that doesn't work anymore. But also, they still have some limitations, like the Intel hardware features for that have limited stack trace depth, I believe. There are some problems with it.
You said not to use Valgrind, so why not?
I mean, Valgrind is really interesting. It's basically a simulator for a CPU that runs your code on the simulated CPU. which is really cool tech, but the problem is that it doesn't really have to do much with how it happens in real life, because Valgrind, specifically CallGrind, which is the profiler in the Valgrind suite, it can only really look at instructions retired. So we can tell you this function costs twice as many instructions as this other function, but that's not really representative of performance. It doesn't mean that this function was twice as slow, because functions have different costs. You can have an add is faster than a divide, and a divide is faster than fetching from memory, for example. So these are things that Valgrind cannot really do much about.
How about Intel vTune?
I don't know what that is.
Me too. Okay. What about C-states during performance benchmarks? As far as I know, modern CPUs enter C-states very aggressively.
Well, that's interesting. I don't think I had to worry about it. Like when I applied the tips that I listed, and I had pretty reliable performance. So would be interesting to hear about that. But personally, I haven't really had problems with that.
Does perf have some sort of a GUI viewer that can display a call graph and annotate C code, like key cache grind or Valgrind?
Yeah, so I don't know, there's one that can do both. Like I showed you that there's the Firefox profiler, for example. There's a few others, and this is nice. You can see a nice call tree here, for example. But perf can actually annotate. I forgot to mention it. Thanks for reminding me. Let's record it again. And if you go into a function, you can tell it to annotate, and it disassembles the function and actually shows you how much time or how many samples were taken at each instruction. So that's pretty useful.
The most important question: what distro and what shell are you using?
I'm using Arch with Z shell. That's basically it. By the way.
By the way. Okay, so I like you. That was Krzysztof Biegański. Thank you very much for being our sponsor this year.
Thank you.
Thank you, Antmicro. 7 minut przerwy.